Hello and most welcome to 1264. And as you can see, we have gotten some snow. Some parts of the country it's a tremendous snowfall and on the verge on disaster in the capital and the island of Gotland. But here I'm safe inside the tropical house in Gothenburg, so-called palm house. As you can see, it's incredibly lush. I even had to take my sweater off. Look at that wondrous specimen. Do you think it's made by laws? Statical, permanent, immutable laws? Or is this the wonder of time? It makes a big difference, I would say, to how you perceive the world in a cold way or in a warm way. It's a modus of being, or a modus, as Roberto Unger would say, of not being as well. Look at that beauty here. I will continue where I took off in 1263, and we are presently at page 188. From the longest read through ever, I think. The history of this series lasted years now. The significance of these differences in the interpretation of general relativity for our argument is that a combination of special relativity with the FRWA and related solutions to the field equations fails to exclude preferred cosmic time, or more generally, to deny or diminish the reality of time altogether. These time-denying conclusions follow only when we add the third element, the conception of space-time, as well as the spatialization of time that is implicit in this conception, with its revealing spatial metaphor of time as a fourth dimension. This conception in turn yields the block universe view in cosmology, the view of space and time as a single reality, or a single system of causal events. So that an event taking place in time can be represented as a point in space-time. The block universe view can be immediately recognized as a successor to Laplacian determinism, except that it implies even more strongly than does Laplacian determinism the essential unreality of time. Not just the non-existence of cosmic time. The block universe does more than place the early history of the universe beyond the reach of explanation, as happens with the inference of an initial infinite singularity. It contradicts altogether the idea that the universe has a history. It does so by translating historical change into non-historical structure. Moments in time into points in space-time. This third piece in the prevalent understanding of general relativity and of its cosmological implications differs from the other two. Incorporation of the confirmed insights of special relativity and appeal to an initial infinite singularity in its character. Special relativity is a scientific theory about the relativity of inertial frames, richly confirmed by empirical and experimental evidence. We can best understand the initial infinite singularity for its part as a mathematical inference from the field equations of general relativity, suggesting the limits to their domain of application. The spatialization of time, the third part of the dominant approach to general relativity, in turn combines two distinct elements. They enjoy radically different degrees of empirical grounding. The first element is the subsuming of Newtonian gravitation within a theory that explores and explains the structure of space. Space ceases to be an independent and invariant backdrop to physical events. Gravitation becomes a name for the reciprocal interactions between matter and space. The second element is a metaphysical vision according to which time is best regarded as an extension or an integral feature of space, varying with space and having no independent reality of its own. Its existence and its flow are, on this account, illusions, as the block universe development of general relativity makes clear. The exclusion of cosmic time works as only the first step in the exclusion or radical diminishment of time altogether. The note here from Einstein. Einstein himself rejected efforts to represent general relativity as committed to the spatialization of time. In his review essay à propos de la déduction relativiste de Monsieur Emile Mangabeira, he wrote, "Furthermore, Mangabeira correctly stresses that many presentations of the theory of relativity incorrectly speak of a spatialization du temps, of time. Space and time are indeed fused into a unified continuum, but this continuum is not isotropic. Indeed, the character of spatial contiguity remains distinguished from that of between two contiguous world points. The tendency he denounces, though often latent in the mind of the physicist, is nonetheless real and profound, as is unequivocally shown by the extravagances of the popularizers, and even of many scientists in their expositions of relativity. Quite a surprise. A mathematical conception expresses the metaphysical vision. It represents space-time as a four-dimensional pseudo-Riemannian manifold. The manifold can be sliced in an infinite number of ways by alternative global space-time coordinates. None of these coordinates enjoys priority. None describes a preferred cosmic time, the time of a universal history. That we should not confuse this second element, the metaphysical vision and its mathematical expression, with the first, but should understand it as the supra-scientific proposal that it is, and can be shown by considering the wholly different relation of each of these elements to what are taken to be the empirical supports for general relativity. These supports bear directly only on the structure of space. They bear on the structure of time, not at all, unless it is already assumed that space and time are inseparable, and that time is simply an extension or modification of space. Such an assumption, however, has no basis in any of those empirical tests of general relativity. Its association with general relativity is the product of a metaphysical bias. A bias against the inclusive reality of time. This bias has accompanied, with certain exceptions, much of the history of modern physics. It has been inspired by a view of the relation of mathematics to nature and to science that we later criticize. None of the classical empirical tests of general relativity the perihelion precession of Mercury, the deflection of light by the sun, and the gravitational redshift of light have any direct or proximate relation to time, or any reliance on the notion of Riemannian space-time, and to Minkowski's geometrization of time. They are all fully accounted for by the geometrical or spatial reinterpretation of gravity, and by the relation between the placement of matter in the universe and the geometry of space. They need not to be interpreted as contradicting either the independent reality of time or the existence of a preferred cosmic time. Of the post-classical tests of general relativity, such as gravitational lensing, frame dragging, and observation of binary pulses, only one, Shapiro's time delay test, confirmed by very long baseline interferometry, has any close relation to Riemannian space-time. Even this test, however, with its prediction of so-called time dilation in the movement of photons close to the surface of the sun, can be accommodated by the part of general relativity bearing on the interaction between the physical nature of light and the gravitational potential of our star. It requires no reliance on the impulse to render time spatial. This impulse betrays a metaphysical idea from which the hard empirical core of general relativity can and should be rescued. It is true that the description of these observational tests is commonly couched in the language of geodesics of a space-time continuum connected with a supra-scientific program for the spatialization of time. In every instance, however, even the aspects of these tests involving time dilation can be fully accounted for by the relativistic way of thinking about matter, motion, gravity, and space, and the effects of velocity and gravity on the movement of everything, including clocks or cells in human bodies, or our biological clocks. There is nothing in these tests or in what they test that require us to make the extra leap of regarding time as a merely local extension of space, or as an extra and inseparable dimension of a space-time continuum. The identification and criticism of this element of supra-empirical ontology in the general relativity is consistent with acknowledging that the theory invoking this ontology may be very successful in its core domain of application, with the result that the supra-empirical leap may seem to be supported by empirical observation. However, it is no more true that the successful application of general relativity to this domain vindicates the metaphysical conception of Riemannian space-time than it would be justified to say that the similar success of classical mechanics in its central realm of application vindicated Newton's picture of a world of interacting forces and bodies against an independent background of space and time. In each instance, the experience of reaching the limits to the domain of application precipitates a characteristic question for natural philosophy. When and to what effect the marriage between the empirical substance or residue and the metaphysical vision to which it is wedded should end in divorce. This line of reasoning becomes easier both to understand and to accept once it is demonstrated that the framework of general relativity can be restated in an equivalent vocabulary such that the choice between the two vocabularies is neutral with regard to the empirical observations. We have Julian Barber's shape dynamics related to Juan Maldasena's gauge gravity duality, trades the gauge invariance of the predominant interpretations of general relativity for a different gauge principle, that of local changes of a scale. It is not crucial to this proposal to divorce the empirical content of general relativity from the project of spatializing time that any particular such equivalent formulation be true or successful as a scientific enterprise in its own right. What is decisive for the immediate purpose is that the discussion of such formulations reveals the gap between what we know for a fact and how we choose to interpret, frame, or represent our empirical findings. I am now able to begin answering the questions about the extent to which the argument of this book contradicts general relativity with regard to full acknowledgement of the historical character of the universe. To the inclusive reality of time in general, and to the existence of a cosmic time. The answer is that the argument contradicts general relativity as a general relativity is often represented. However, it does not contradict a version of general relativity that has been subject to 3 sets of clarifications. I have sketched in the preceding paragraphs the reasons for these clarifications. First, the local relativity of simultaneity must be qualified by recognition of the existence of a preferred state of rest in the universe, and thus as well of preferred observers. Such observers might in principle see the universe averaged over a suitable large scale from a vantage point undistorted by local inhomogeneity and anisotropy in the disposition of matter. They could in principle determine whether an event happening in Andromeda was happening before or after on the cosmic line an event taking place in NGC 3115, and they would have reason to credit their observations as in correspondent with the cosmic timeline. That there can be such observers depends entirely on certain facts about the constitution of the universe, such as its relative homogeneity and isotropy. It cannot be inferred from a priori considerations that we on the planet Earth failed perfectly to figure among such preferred observers in no way contradicts these limits to the relativity of simultaneity or their implications for the existence of cosmic time. We can in fact correct for the movement of our planet and approximate the circumstance of preferred observation. Second, the inference from the field equations of general relativity to the notion of an initial infinite singularity must be understood as a mathematical revelation of a certain temporal limits to the domain of application of general relativity. It must not be interpreted instead as a conjecture about an actual state of the universe, either in its earliest formative movements or in its subsequent evolution. Third, and most importantly, general relativity must be reformulated without the addition of the Riemannian space-time conception. The disposition to spatialize time, or the block universe view, none of which are vindicated by the empirical and experimental evidence, adduced in favor of general relativity. The metaphysical gloss must be lifted from the empirical theory, with the result of suggesting a redirection of the agenda of cosmology. These multiple qualifications represent no small adjustment to the common understanding of general relativity. Yet they are all justified by what cosmology has discovered about the universe and its history. They are justified as well by the need to resist the seduction and corruption of physics by mathematical ideas. For instance, the representation of the infinite, that have no place in the workings of nature. These justifications are no mere grab bag of unrelated findings and ideas. Rather, they compromise different aspects of the same basic insights into the historical character of the universe, to which even the most ambitious structural theory of nature must accommodate, if it is not to misrepresent its subject matter. I now address more briefly the relation of our argument about time and the historical character of the universe to quantum mechanics. With respect to the quantum theory, as with regard to general relativity, the issues is whether what the theory has discovered about the vicissitudes of nature contradicts the claims that we make here. my discussion will be more compressed, both because quantum mechanics bears less directly on this part of our argument than does general relativity, and because, to the extent that it does bear on the argument, Smolin will address its significance later in this book. Like general relativity, quantum mechanics is a structural rather than a historical theory. It presents no account on transformation in natural historical time. It is true that the time-dependent Schrödinger equation, when taken in tandem with thermodynamic principles, creates a basis for grounding transformation and time in the minute workings of nature, and for connecting change at the atomic scale with change in the macroscopic world. Why? That this set of implications is nevertheless insufficient to serve as a basis for the understanding of temporal processes on the scale of the history of the universe was long ago shown by the Wheeler-de Wit equation. This equation suggests that once applied to the whole universe, quantum mechanics has no place for time. Its cosmological application results in a quantum mechanical equivalent to the block universe view, inspired by the most prestigious interpretations of general relativity. Barber and others have developed the implications of this view for denial of the reality of time. Quantum mechanics and its crowning achievement, the standard model of particle physics, have been richly confirmed by empirical and experimental results. Can they be legitimately invoked as an objection to the view of time and of universal history that we advance? They cannot, because quantum mechanics is essentially incomplete and therefore approximate in two distinct but connected ways. In the first place, it is incomplete because its account of its subject matter, the operations of nature in the cool-down universe at the most rudimentary level, fails to yield any determinate picture of these operations. Not only must it deploy stochastic rather than deterministic reasoning, but it must also appeal in this reasoning to the idea of the infinite. Infinite possible configurations rather than the initial infinite singularity that has been inferred from the field equations of general relativity. However, here as always in science, the infinite is not a physical reality. It has no place in nature. The infinite is the measure of our ignorance. The appeal to stochastic reasoning under cover of the mathematical but not physical or natural idea of the infinite was the legitimate target of Einstein's objections to the quantum theory that he had helped create. The effort to redress this ignorance has set some on the search for hidden variables that could help replace probability with determination and conjectural infinity, with a view of what happens when and where at the cosmic scale. The hidden variables theory is capable of accounting for the nature and effects of these hidden variables could only be relational views. They would show how the particles, fields, and forces studied by quantum mechanics relate through reciprocated action to features of the universe that have remained outside its scope of inquiry. Here, however, we come to the second way in which the quantum theory is incomplete and thus restricted in its domain of proper application. It is incomplete because it is unhistorical. one might argue that quantum mechanics deals with all of nature, albeit at a certain level, the level of the most basic natural processes, rather than with some patch of nature. To that extent, it would be untainted by what I earlier called the first cosmological fallacy, applying a method suited to explore part of nature to the study of the whole universe. However, even if one accepts this response, there is no adequate sorry. Très joli. To that extent, it would be untainted by what I earlier called the first cosmological fallacy, applying a method suited to explore part of nature to the study of the whole universe. However, even if one accepts this response, there is no adequate defense against the accusation of committing the second cosmological fallacy. Why? Quantum mechanics is also incomplete because it treats as the intrinsic and eternal furniture of the universe the law-obeying and discriminate structure that the cooled-down universe displays. What cosmology has already discovered about the formation of the universe suggests that the elementary structure described by the standard model of particle physics did not always exist. For example, a crucial moment in the formation of the universe, the moment called decoupling, occurred when the atoms became stable. If this structure once did not exist or took different form, it may later in the history of the universe also differ. In regions of the cooled-down universe, such as in the interior of black holes or in the remote future, our experimental technology, including our particle colliders, may develop to the point of allowing us to simulate aspects of these extreme states of nature. Quantum mechanics, as it is now understood, would then become the theory of the elementary workings of nature in one of the phases of nature. If we make the analogy of at cosmological scale to the local physics of phase transitions. In this inquiry, as in every department of science, to understand phenomena is to grasp what they have become or can become under certain circumstances or provocations. Structural understanding is ultimately subordinate to historical insight. The hidden variables theories needed to continue the work of quantum mechanics and replace its reliance on stochastic reasoning and on the mathematical infinite, must therefore be temporal as well as relational. The science of which they would form part would be informed through and through by a temporal naturalism. Until we come into the possession of such a science, we can have no confidence in the cosmological applications of quantum mechanics. These applications will, on account of the twofold incompleteness of the underlying theory, continue to point in the opposite directions, either supporting or denying the reality of time, and either accommodating or resisting the discovery that the universe and all of its regularities and structures have a history. It is common to suppose that both the reality and the direction or arrow of time need no basis of support other than the long established principles of thermodynamics. It is true that the special and seemingly unlikely circumstances making an entropic process irreversible may play a role in the evolution of the universe. Great homogeneity and consequent low entropy in its very early history. It is also true that the temporal asymmetry of these macroscopic processes may be anchored or prefigured in particle physics by the so-called CP violations of the weak interactions. Nevertheless, thermodynamic principles are insufficient to provide a basis for foundational thinking about time for three reasons. The first reason is that an account of the basis for an arrow of time cannot suffice as a response to ideas that deny the reality of time altogether, or that treat special and general relativity as insuperable obstacles to the affirmation or preferred cosmic time. The second reason is that statistical mechanics is, by the character of its theories, equations, and procedures, a study of local realities in the universe. Like classical mechanics, it works by applying invariant laws to changing phenomena within a configuration space defined by stipulated initial conditions. The cosmological application of such a theory takes it to a level at which no such distinction between initial conditions and timeless laws makes sense. The configuration space becomes the entire universe. There can be nothing outside it other than the imaginary universes of the multiverse conception. The initial conditions are simply the state of the whole universe at some arbitrary point in its history, the same as the configuration space, only at any earlier time. Such a cosmological extrapolation of the local theory represents an instance of the first cosmological fallacy. The third reason is that entropic processes are not in fact irreversible except in certain circumstances. Conversely, the laws of motion in classical mechanics becomes irreversible as soon as we add certain real-world features of events to the circumstances that they are used to explain. The contrast between reversibility in classical mechanics and irreversibility in statistical mechanics is circumstantial and relative. Any understanding of how a diminution of entropy at a cosmological scale could come to be irreversible presupposes the reality of time and the historical character of the universe more than it explains them. One way of explaining irreversible cosmological entropy invokes special circumstances in the very early universe. If these circumstances are not hidden behind the impenetrable screen of initial infinite singularity, they demand historical explanation. A previous state of affairs must explain how they came to be what they were. Such an explanation invokes time, and at least at the formative moment, a line of preferred cosmic time. Even if by the prevailing interpretations of general relativity, the world later ceased to have a time in common. Another explanation appeals to a directional law that, at least at a cosmological scale, we would have to add to the standard repertory of thermodynamics, the better to ensure an asymmetry between past and present. Such a law, however, is only another name for time, rather than an account of its emergence out of putatively more fundamental physical realities. We require a deeper and more general basis for our understanding of time than any that is offered by statistical mechanics, and by the attempt to give it a cosmological application. Thus far, I have considered reasons to believe in the inclusive reality of time and in the existence of a cosmic time
that have to do with particular features of the observed universe, as well as with the discovery that the universe has a history. I have discussed whether these ideas about time conflict with established empirically supported science, primarily general relativity, the body of ideas with which our claims seem to be in greatest tension, and secondarily special relativity and quantum mechanics. With regard to which the conflict is both less obvious and less acute. These are not, however, the only reasons to adopt the views about time that we propose. There are also reasons of a more general character. Proposals in natural philosophy and in comprehensive scientific theories should be evaluated by the totality of their advantages and effects, including the intellectual opportunities open up by the research agendas that they inspire, as well as by the explanatory power and the empirical foundation of their component pieces. To deserve influence, such general considerations should retain a connection to empirical challenge or confirmation. The power of comprehensive use needs to be assessed as a whole by comparison to rival research programs. Among general reasons of this order, it is in turn important to distinguish between those that have to do with some understanding of the nature of the phenomena studied by the research agenda, and those that rely on assumptions about science itself. We should entertain this second class of general reasons about the requirements of scientific practice with parsimony and suspicion. There exists no single uncontested and universally applicable way of doing science. Method must follow vision rather than the other way around the defense of a program of inquiry on the ground that it, and it alone, embodies the correct practice of science, can easily serve to mask metaphysical prejudice and to inhibit the dialectic between vision and method. An example of immediate pertinence to our argument is the commonplace idea that science cannot dispense with the idea of a framework of immutable laws of nature. Whether there is such a framework is a matter of fact, regardless of how difficult and perplexing the matter of fact may be to investigate. A more complicated example is the attempt to entrench a particular view of causal connection as intrinsic to human understanding, as Kant did, against the background of Newton's physics. Very important, this last. It's incredibly sharp. Nevertheless, there is a legitimate residue in such general reasons having to do with scientific practice. It is the preservation of openness to empirical and experimental test. However varied and oblique the testing may be, an objection to the invocation of an infinite initial singularity as something more than a mathematical reductio is that it places a range of phenomena beyond the reach of further inquiry. An objection to the idea of a plurality of causally disconnected universes is that it multiplies entities that cannot, even in principle, be investigated, confirmed, or excluded by empirical tests. It disposes of an explanatory embarrassment at the cost of creating a much larger one. By contrast, the argument in natural philosophy and in cosmology that we develop here is open on all fronts to empirical consequence and challenge. As in any such ample theoretical view, some parts of the system of ideas are much closer to empirical implication than others. We nevertheless count it as a fatal objection to a view that it be especially in principle, immune to investigation of the fact of the matter. Incredibly important. It blocks out all investigation. By contrast, the argument in natural philosophy and in cosmology that we develop here is open on all fronts to empirical consequence and challenge. As in any such ample theoretical view, some parts of the system of ideas are much closer to empirical implication than others. We nevertheless count it as a fatal objection to a view that it be, especially in principle, immune to investigation of the matter. This remark leads into the first and more legitimate set of general reasons to prefer an agenda of theory and research to its rivals. Reasons that have to do with the phenomena that it addresses. An advantage of the ideas about the inclusive reality and the existence of global time that we propose is that they fit much more easily than do their rivals with other views about the singular existence of the universe and the selective realism of mathematics. There are, we argue, independent reasons to hold these other views about the solitary character of the universe and the imperfect relation of mathematics to nature. The singular existence of the universe, the inclusive reality of time with its implications for the mutability of the laws of nature, and the selective realism of mathematics are intimately related and overlapping conceptions. Haven't I said that before? Sorry to remind. It is not easy to adopt any one of them without accepting the other two. The thesis of the inclusive reality of time is connected to the notion of the singular existence of the universe because it makes it possible to put the idea of succession of universes or of states of the universe without break in causal continuity in the place of the idea of plurality of causally unconnected universes. If everything that has ever happened or will ever happen can be placed on a single time chart, the import of the concept of preferred cosmic time, not only will events in the present universe fit on this chart, so in principle will events in every universe that preceded it, if such universes have existed. If, according to another attribute that we claim for time, time is not emergent, its flow will be uninterrupted by a succession of universes or of states of the universe. Indeed, there is such a succession. There will be no interruption of causal continuity, even if, for example, successive universes undergo periods of extreme density and temperature. It will continue its uninterrupted progress through other periods in which the universe cools down and expands, acquires a discriminate structure, and sees a distinction established between states of affairs and laws governing them. Expressed in this abstract and comprehensive form as the natural philosophical basis for a cosmological program, these ideas may at first seem to be entirely speculative and beyond the reach of empirical test. Yet they can be falsified by a single observation or experiment suggesting the disappearance, emergence, or interruption of time in any of the states in which nature presents itself, local or cosmic. These conceptions and arguments do indeed fail to take issue with theories that deny the reality of time altogether, or that reduce time to a series of frozen configurations of the universe. However, they fail to take issue only because the time-denying accounts makes themselves invulnerable to empirical test. Such theories set themselves against empirical challenge by redescribing in time-free language all the observations and experiments that we perceive as taking place in time. By the same token, they render senseless the discovery that the universe has a history. For if history means anything, it means causal succession in real time. The quasi-empirical view of mathematics, the view of mathematics as a simplified representation of the most general aspects of nature, which then takes off on its own, even when its inventions have no counterpart in the natural world, denies to mathematics any privilege to reveal the intimate nature of reality. This deflationary approach to mathematics is similarly connected with affirmation of the reality of time. This connection remains fundamental to the understanding of both mathematics and nature. The relations among mathematical propositions are timeless, even when, as in the calculus, they are used or were even devised to represent temporal events. If everything in nature, even the laws of nature, is time-bound, a gap opens up between what is natural and what is mathematical. At a minimum, there can be no mathematical object that is homologous to the natural world. More generally, the abstraction of mathematics is closely related to its timelessness. Its immediate subject matter is not the real world, but an imaginary proxy for that world, bereft of both time and phenomenal particularity. Disregard for phenomenal particularity is closely related to denial of time. These views about mathematics also serve an agenda of empirical and experimental reason for a straightforward reason. They oppose the legitimacy of any attempt to use mathematical reasoning as a substitute rather than as an instrument for empirical inquiry. They render empirical the question of whether any given mathematical conception is or is not realized in nature. They help explain how mathematics can be so useful despite its divergence from nature and because of that divergence. The argument composed by our three central ideas supplies the substance of the temporal naturalism that we advance. Such a naturalism supports the continued transformation of cosmology into a science that becomes central rather than marginal to physics. It informs conceptions that are hospitable to a fuller reception of the discovery that the universe has a history and that everything in the universe changes sooner or later. I'll put a point there. I'm going to make my take of today of this. Well, physics has been criticized before for becoming too mathematical, but I would say all those criticisms have lacked argument, substance, force. They have been gut reactions. This is entirely different. It shows it is a mistake in perception, in understanding. It's a mistake in order, and once established, it is impossible to uncover. But we are all, I would say, in the Western Hemisphere, completely used to understand physics as mathematics. And for some reason, mathematics is what tells what is empirical or not. And of course, that is not a good situation. Mathematics is a tool. It's a fantastic tool. But empiry must be the leading. Our wanting to understand the world should not have metaphysical presuppositions of structure embedded in them. And it should definitely not have the idea that structure becomes an a priori thing. And it's also obvious here now that Kant had Newton underneath him for all of his philosophy. Could be the sharpest criticism I ever heard about Kant. It is devastating. But let's think about that in a discussion. It needs to be pondered properly. I would take you around to see what nature does produce, which is not structured necessarily. It shows punctuated evolutions, shows force, shows things happening. It shows that not all is decided already from the outset, that there is creativity, and that the world contains incredible beauty, and that this plant is not a consequence of cause and effect. It is made by time, and we cannot say what time is beforehand. We cannot force time into our understanding, because by doing so, we make a tremendous attack on the understanding faculty itself. Yes, mathematics can absolutely be used to excellence in small situations, as long as they are smaller. Yes, doesn't have to be very small, but smaller than the universe. Look at this. Smolin himself admits that what from beginning drew him to physics was the beauties, the symmetries of Albert Einstein. And now he changed his mind, and I would say in the most decisive way I ever encountered. It is just fantastic, and look at this. Is it even possible? These are for flies to get into, and once they get into the lower part of this, as you can see, they don't get out. They will be stuck there. As we are stuck in the current thinking, drowning. And it's also interesting, I think many people have felt the modern world to be two aspects, I would say, either too small, unfitting for their ideas,
and incredibly limiting. And others have felt and adjusted their souls to become smaller to fit the world. And I think it could be that sort of mode of being that led Lee Smolin from the beginning to physics. A limited soul that wanted to see limitations and name them beauty. Two divergent lines that here, in a way, conflate to make one single problem. And the ways going about these people done, either by not criticizing or criticizing, have all missed the point. Because the point is not that there is something wrong with the world or how we interact with the world. The problem lies in how our thinking has changed during time and become less and less accepting that time itself can change. And therefore we have become unchangeable, fixated, tensed, and we friction against the world. We don't take it in, we do not take it in. We no longer accept experience as it is. We block it out, we tense, we become stiff-necked, inhospitable to everything that the world has to offer. There's too much light coming out of the windows, but you can still get some idea of the shape. All that snow reflecting light from everywhere. He gives us freedom. Lee Smolin shows that there is freedom in thinking, and that freedom cannot be acquired by criticizing, arguing, as people tried now for 150 years. It needs to be understood, and someone needed to find where was the problem. Something illicit had been done. Isn't that fantastic? I think you spontaneously can think. Because no longer is the fault ours or in the world. We do not need to have any guilt, neither do we need to criticize the world. A mistake has been made and it can be explained, opened up, and nothing has to change. We will just get more empirical understanding of the world. And no longer the arguments and feelings, I would say, of the postmodern needs to prevail. And the idea that everything is relative, that there are no truths, and that our very mind is something not of this world, but otherworldly. Because we make our soul otherworldly. And no wonder the human soul has become so hard to reach because of that tendency to make the soul transcendental. It goes hand in hand with Richard A. Lind, the transcendental consciousness or reflective consciousness. It's this being fixed, fixation of stature, attitude, thinking, It makes a harder thinking, harder in like stone-like thinking, not flexible, not viscous like time itself, but instead a Newtonian fixation. Poor old Kant, he was trotting the bridges of Königsberg, not knowing that he was actually trotting on a ground made by Sir Isaac Newton quite some time before, and that his path that he took in his thinking was not as free as he thought. No, just on the contrary, it could be that all his conclusions are actually caused by putting oneself in a Newtonian paradigm, and then inside that paradigm make philosophical conclusions that would turn the philosophy of Immanuel Kant to only a word game. I say thank you very much and have a very pleasant afternoon, that is.